This is Linked Data Engineering, lecture number 2, RDF and RDFS. In this part of the lecture, we want to talk about logical inference and the possibility to draw conclusions based on RDFS. So, if you see something like that, what knowledge is in there? What can you see? So let's start in this interesting graph representation of RDF and RDFS with the planet Pluto that you see here on the left side. So we see here that Pluto is of type planet, and we see also that planet is a subclass of celestial body. On the other hand, we see that Pluto is labeled or has the name Pluto, and we see a discovery date which is 1930, as we see here. And then we see that there is a moon, it's called Charon, and this moon also is a celestial body and it's a satellite of Pluto, and we see that Pluto has a discoverer who is Clyde Tombaugh, and Clyde Tombaugh is of type person. So this is a lot of knowledge in there, but what can we make with it? If, for example, some program or some machine is receiving this kind of knowledge expressed in RDF, RDFS, what kind of deductions can we draw from that? Okay. So usually the semantics of a term from an RDFS ontology you hear for the very first time, but you will see that exactly this notion for knowledge representation will occur much more often in the future of this course. So the semantics of a term is given in terms of its properties and values or its instances. Okay, so what's so special about RDFS semantics if you compare it to traditional data definition languages? So in difference to them, RDFS is based on a formal semantics, which is really, really important. Simply because a formal semantics or a formal mathematical logic, a formal mathematical model, enables RDFS to draw valid and sound logical inferences from given knowledge, to create new knowledge which is valid, which really holds. And for this, of course, you need a mathematical model behind the data definition language, and this exists here. And we will see how we can exploit this, how we can make use of that. Some examples here. For example, if I say Pluto is of type planet, so Pluto is a planet, this means nothing else that Pluto is an element of a class which is called planet. So you see here a pseudo-mathematical or set-theoretical description of exactly that fact. So Pluto is element of planet. Another thing would be planet is a subclass of celestial body. You can express this, of course, also with a subclass relationship from set theory. You say planet is a subclass of celestial body, as you see here in blue on the right side of the slide. And the same holds for example, for property hierarchies. If I define artificial satellite of as a subproperty of satellite of, then you can simply translate this also in set theory. And this process of translation is a way to define a semantics with mathematical means. And this kind of defining a semantics is called model theoretic semantics. So you simply interpret the meaning of your constructs by building a new model, a simpler model, on which it is based on. This is model theoretic semantics. Don't worry about that. It's only to make sure that there is a solid mathematical foundation behind that. More interesting for you will be, what can I do with it? And this we will see next. Okay, we have a given structure, and now we want to know what kind of conclusions can we deduce with RDFS. So let's have a look here. We have Sputnik 1, which is an artificial satellite of Earth, and we see here it's of type artificial satellite, and artificial satellite is a subclass of satellite. What we can see here, we know this from the subclass relation, is that we can deduce new facts here from the class hierarchy, simply because every instance of the class artificial satellite must be contained also in the class satellite, means that we can deduce the fact that Sputnik 1 is of type satellite. This is a valid and sound conclusion. And this is based on the fact that there is some mathematics behind there. You can, or you could express it with the following rule, that you say for all instances I that you are looking at, and you have two classes, C sub 1 and C sub 2, it holds that, and now there is another way to write triples here in a mathematical setting. I simply write it with T, and then in parentheses I have the triple. So I say if there is a triple that an instance is of type C sub 1 and C sub 1 is a subclass of C sub 2, then, so this is a mathematical implication, then it holds that I is also of type C sub 2. This would be the mathematical expression of how I can deduce new knowledge and how I can make sure that the subclass relationship exactly holds. So this is quite nice, of course. But there is more. Look at the following fact. We have here the definition of a property, which is DBO satellite of. This is of type property, and it has a domain and a range, and both is celestial body. And then we have a statement, we have a fact which says Pluto is a satellite of something, we have no idea what it is, so it's a satellite of blank node. What knowledge can I infer from that? Yep, I can make use of the domain and range restriction of that property. For sure now I know, simply because Pluto is connected via a specific property to another instance, I can deduce that Pluto must be of type celestial body, because this is the domain of the property satellite of. So this is an interesting deduction that I can draw. I can simply deduce a class membership from this domain restriction. Of course, I can also rephrase this in a mathematical setting. So if I do this in a mathematical setting, I would say for all instances I sub 1 and I sub 2, all classes C sub 1 and C sub 2, and all properties P, the following holds. If I have the triple I sub 1, P, I sub 2, which means I sub 1 is connected via a property P to another instance I sub 2, and we have a domain restriction on P, which says that the domain of P must be C sub 1 and the range of P must be C sub 2. This is the second line. Then it holds that, or that this implies that I sub 1 must be of type C sub 1. So this is the first thing that we see here, the first deduction that we can draw. And of course we can also draw the other conclusion that here the range is bound to a specific class, so that I sub 2 must be of type C sub 2. In our example, it means that the blank node must also be of type celestial body, because this is restricted by the range restriction for the property. And then, of course, I have two new facts. These are class membership facts for two instances in my knowledge base. And this is so-called hidden or implicit knowledge, and I can deduce it. And I can deduce this in an automated way, simply because there is a formal semantics below. This, of course, is something nice. Let's have a look at the last example. Here we have a sub-property relationship. So we have here, let's start with the first line, the upper line. We have a property which is called satellite of, which is bound as domain and range to celestial bodies. And we say artificial satellite of is then a sub-property of satellite of, simply because that artificial, this is then bound to domain and range restrictions. Domain is then artificial satellite, and the range is some kind of celestial body. And then we have the A box. This is the last part, the lower part of the graph, which says that Sputnik 1 is an artificial satellite of Earth. And of course, simply because artificial satellite of, we can draw immediately these type inferences of Sputnik 1 and Earth. But we can do more. Simply because of that sub-property, we can deduce a new fact which says that Sputnik 1 must also, of course, be a satellite of Earth. Not only a artificial satellite, because artificial satellite is simply a specialization, it's a sub-property of, and simply because of this class hierarchy means that all things which are connected via the more specific property are also connected via the more general property. So this is the way how we define this, and this can be immediately deduced. The formal representation of that again would be for all instances I sub 1 and I sub 2 and all properties P sub 1 and P sub 2, it holds the following, that if two instances I sub 1 and I sub 2 are connected via a property P1 and P1 is a sub-property of P2, it holds that also I sub 1 must be connected to I sub 2 via the more general property P sub 2. These are the conclusions that I can draw based on RDF, RDFS with the help of RDFS semantics. Of course, this is not very much, but this is more than you can do with some of the other data definition languages. We will see where are the limits of RDFS later on, and we will also see how we can further refine knowledge representation and how we can put more knowledge, more constraints, more interesting restrictions to this kind of knowledge that we define to make use of it. But we will do this later on in a later part of the lecture. Here now we will conclude the first part of RDF, RDFS, because we have defined all language constructs that are possible. We have looked at RDFS, and also we have looked a little bit at the formal model behind and the logical conclusions we can deduce from it. In the next part of this lecture, you will see how RDF can really be employed in the web, because in the web, you know, usually documents are represented in HTML, and in HTML probably you don't see RDF and RDFS, but there is a way to get RDF into these HTML documents, and this is called RDFA.